Hey everybody, welcome to Math 20-1. We are starting with the quadratics unit, and lesson 1 is Introduction to Quadratic Functions. Remember, before you start, to have your workbook printed off, maybe have a pen, your graph paper, and make sure you're in a quiet area where you won't be disturbed as you work through the video lesson. Remember, at any time you can stop the video and just get yourself caught up. Also remember that anytime, feel free to contact your teacher about any problems you may be having so that you get those cleared up right away and keep moving forward. So let's go ahead and get started. Now over here on the right hand side, there is an Activate section. This would have been gone over in the Activate section of the course website. So we're going to skip on over that and head right into quadratic functions. Now, a quadratic function is a function that has an independent variable, mostly denoted by x, with an exponent of 2. So, right there we go. And the function of a quadratic, x must have an exponent of 2 in at least one of the terms. However, no exponent shall be greater than 2 in any term, and only whole number exponents in any term. In other words, no fractions, decimals, or negatives as exponents on x. In other words, a quadratic function must have an x squared term and may have an x term and a constant term. In general, a quadratic function can be written like this. This is standard form. Y equals ax squared plus bx plus c, or as we looked at in the Activate section, we can use function notation and say f of x equals ax squared plus bx plus c. And remember that a, b, and c must be real numbers. So let's look at some examples. In this one here, notice we have the 2 on the x, therefore it's a quadratic function. This one here, the highest one is a 2, which is in that first term of 3x squared. And this one is okay because even though it doesn't have an exponent on it, we know it's 1 and a constant term of 1. Now over here we have y equals 1 minus x squared. Now even though the x squared term is second, that's okay too, because we can actually just change the order around. And in the last one here, y equals negative 4x squared minus 2x. This one is still a quadratic. Even though it doesn't have a constant c, we know that in this case, the c value is actually 0. And fun fact, the name quadratic actually comes from a Greek word meaning to make square. We use it here because x is being squared. Okay, let's move on and look at some examples. So question 1 here asks, which of the following are quadratic functions and how could you check? If it's not a quadratic function, state the reason why. So let's look at what we have. First thing, it has to have a square. So let's look at this one. Indeed, we have a square in it, and that square actually has to be the highest. So no other terms can have an exponent higher than 2 on the variable. And this case, that's true. This one has a nice little constant, so we know that this is quadratic. In this one here, again, we have a 2 right here. And this one is a 1. It's that hidden one. We don't write it. It's implied. And therefore, this being the highest 2, we can say that that is also a quadratic. For this one right here, y equals 3 root x minus 5x. Well, we can write this in a different way, breaking out some of our exponent rules. We know that a radical can be written as this minus 5x. And even though there does have a 2 in the exponent, it's in the denominator. Therefore, this follows that we cannot call this a quadratic. This one right here, y equals 3x minus 5x squared over 4, well, it has a 2, it has a 1, so the 2 is the highest. The order can be switched to make it first. And even though we have this 4 in the denominator, remember that's really saying 3 over 4x minus 5 over 4x squared. This is just rewritten in a different way. So this is also a quadratic. Now the last one here, it does have 2 as the highest exponent, but the problem is it's in the denominator, which means in this case it is not an exponent. The variable has to be, like in this one, in the numerator. Okay, let's look at question 2. Robin says that y equals x minus 3 all squared plus 4 is not a quadratic because the exponent is not on the x. How could you convince them that this is actually a quadratic function? Well, the fact is the x actually is being squared even though it is not obvious just by looking at it. The reason being is that the x has this minus 3 subtracted to it right here, which kind of makes it look like it's not squared. However, let's see what happens if we expand this function and rewrite it in a different way. So let's start by saying y equals x minus 3 squared plus 4, and expand that x minus 3 squared to x minus 3 times x minus 3 plus 4. Well, let's FOIL that out. Remember, FOIL first, outside, inside, last. So we're going to multiply the first terms of those two binomials to get x squared minus 3x, then minus 3x, and then the last plus 9 plus 4. Putting this all together, we get x squared minus 6x, and 9 plus 4 is 13. And in this form, we can see that this actually does have the square on the x variable, and none other are higher than it. So I hope this is enough to convince Robin. Let's moving right along here. I want you to pause the video for a moment and go ahead and open the practice work on Introductions to Quadratics. The link is in the course website. And I want you to try question 1 and check your answers at the bottom of the page. If you are a synchronous student, you can just skip this. We've done this in class. But for asynchronous students, if this is giving you trouble, I want you to make sure that you are contacting your teacher right away so that they know that you need some help. Okay, now that we know what the equation of a parabola is, and that's y equals ax squared plus bx plus c, we know what that equation looks like. We also want to know what the graph looks like. Well, the shape of the graph of a quadratic function is called a parabola. And parabolas can open one of two ways. It could be opening upwards, just like this one where these are going off to infinity. Or it can be opening downwards, like the blue graph, where the two ends are going off to negative infinity. Well, some key characteristics of parabolas are, regardless if they're opening up or down, they have a vertex. And the vertex is where the parabola changes direction. So for opening up, this would be the vertex right here. And notice this is sloping down and to the right, and then it starts going up and to the right. Whereas for this one right here, it starts by going up and to the right before it gets to the vertex, and then down and to the right after it gets into the vertex. The y value of the vertex is known as a maximum or minimum. If it opens upwards, which is this one to the left here, it will have a minimum value because the vertex right here is the lowest point. So we're just going to write minimum in there. If it opens downwards, well, then it is at the top of the hill. So it is a maximum right there. Now, another special feature of a parabola is what's known as the axis of symmetry. And the axis of symmetry is an imaginary line that cuts the parabola in half. And we've labeled the axis of symmetry right here. And it's this line right there and the line right there. Now, two other very important features of a quadratic function are the y and x intercept. The y-intercept is where the parabola crosses the y-axis. And a nice thing to note about this is that all parabolas or all quadratics will intersect the y-axis. And the form of those points, because it's on the y-axis, that means its x value is 0. And it can have any y value as long as it's a real number. For the x-intercepts, that's a little different. It may have x-intercepts, and we're going to get to that a little later in the unit, but this is where they will be intersecting the x-axis and opposite to what the y-coordinate of it, or sorry, the y-intercept ordered pair looks like. The ordered pair of an x-intercept will be x and 0. So let's look at another example. In this one, it's asking us to complete the table of values below for the two given quadratic functions. And this is an important step in creating graphs, is creating this table of values. We often like to pick a variety of x values and put them into the function to determine the output or y values. Well, the first one is when x equals -4. And so if I just do that up here, f of -4 equals -4 squared, and that equals -4 times -4 is a positive 16. And I'm going to do that for all of these here. Let's do the same thing for -3. F of -3 squared. Oops, sorry, my bad. F of -3 equals -3 squared, which equals, because it's multiplying two negatives together again, we get the positive 9. How about you take a moment to stop the video and see if you can fill in the rest of the values. Okay, so putting that all together, we get 16,941,01496. Notice that little pattern that's going down here. It goes 69410, and then it goes back through those same numbers in the other direction, 149. 16, sorry, my bad. Now let's do the next one. For the next one, we have a little bit of order of operation to consider. For instance, if I want to find g of -4, which is the first one there, and I plug that in, I have to make sure I'm remembering BEDMAS to do my brackets first. That's going to give me negative times -4 plus 1, that's -3. That's squared plus 4. So brackets and exponents. So I have to make that 2 apply to the -3. And a negative times a negative is still positive. So that's -9 plus 4. Now there's no multiplication or division here. So I skip right to addition, subtraction. And I get -9 plus 4, which is -5. I want you to go ahead, pause the video, and see if you can fill in the rest. Okay, how did you do? Again, you might notice there's a bit of a pattern here. It's not as even. It seems to be slightly offset. Notice it goes -5, -5, 0, 3, 4, and then it goes back 3, 0, -5, and then we have these 2 extra points here on the end. The next thing it asks us to do is then to graph both of these functions on the grid. So take your time, make these things ordered pairs. So for instance, our first ordered pair would be -4 and 16, where the x coordinate is -4, the y coordinate or the f of x is 16. So let's go do that. We take our -4, which is right here, and now, 16, that's way off the graph here. So it's going to be kind of like about there. The next one is -3 and 9. Well, I definitely can get that one in. And then -2 and 4. We can definitely do that one. And -1 and 1. 0 and 0. 1 and 1. Notice the pattern happening. And then this one is going to be somewhere off the charts right here. And let's make this one blue. Now this is sometimes the hard part. The idea with drawing these quadratic graphs is to still make them smooth and not like you're connecting the dots. We want to kind of go as smooth as possible, curving along the way as required. And then we curve it down and then curve it up. And it doesn't have to be perfect. There we go. Let's do the next one. Well, this one goes -4, -5. There's that point. -3 and 0. Oh, there we go. -2 and 3. That one's right there. -1 and 4. And oh, now we're turning around, going back down the other way. And if you want to pause the video and try to do more of this yourself, definitely go ahead and do that and then come back and see how you did. And then the 4 and -21 is right off the charts. Let's make this one red. Again, we know it's going to go off the page. Trying to make it as smooth as possible. I know, especially if you're using a tablet, it might not be as easy. And there we go. And put our arrows to show it's going to infinity in both directions. There we go. Nice work. Okay, so let's identify some of these things that we've talked about for quadratics. The first thing we need to do, let's start it with the blue first, so I'll do those in blue. And let's identify the vertex. And the vertex is that turning point. And we know right here, that's where it goes to sloping down to sloping up. So the vertex here is 0 and 0. And then it says, what is the maximum or minimum? Well, again, the minimum y value is y equals to 0 for the blue because it has a minimum. It's opening upwards. Now, the axis of symmetry, remember that's that imaginary line, and we're going to be finding the equation of it. So if I drew a line that cut this perfectly in half, it would go down through here. It's actually on the y-axis. So in other words, this is x equals 0 because it goes through x equals to 0. So note that while it is the y-axis, the equation of the y-axis is x equal to 0. Now let's look at what is the y-intercept. Well, this one, the y-intercept is, well, in this case, it just happens to be the same as our vertex, which is 0 and 0. And the x-intercepts, well, also happens to be there too. So this is a special case where the vertex, y-intercept, and x-intercept are all the same point. Now the same can't be said about this other graph, this g of x. So let's go ahead and do that for this one. We'll do that one in red. So the first thing here we notice is that the vertex is not on an axis or on the origin. It's right here. And its point is -1, that's the x value, and 4, that's the y value. Well, what does that mean about the min or max? Well, because it's opening down, it has a maximum point, and the maximum point is y equal to 4. And, check it out. What is going on right here? What does that tell us about the vertex? Keep that little fact in your pocket. Now, the axis of symmetry of this one is this one here that cuts it in half, and it goes through, I've hidden it pretty well there, it goes through x equals to -1. Again, check it out. Look at what's going on here. Can we see that relationship there? Hold on to that little thought. Keep that for a moment. Let's talk about the y-intercept here. Now, this one is different. The y-intercept of this graph, look at that, is the x still equals 0, but it is 3. There we go. Now, what about those x-intercepts? Well, this one is not like the first one. This one actually has 2. It has one right here, and it has one right here. Let's do the one on the left first. Well, it has an x value of -3, and because it's on the x-axis, the y value is 0. It also has this other one to the right, which has a x value of 1, and again, it has to have a y value of 0. Nicely done. Let's keep moving. Now we're going to head on over to domain and range. Now, you've seen these before, and sometimes we don't always like domain and range. But don't worry. Domain and range for quadratics is actually pretty easy. Remember that the domain tells us what x values are possible. In other words, the ones that we can use. The range tells us what y values are possible. In other words, if we picked any point on the graph the y-coordinate would be part of the range, and the x-coordinate would be part of the domain. So in this course, and this is really a bit of a refresher from 10C, is that we're going to be using two types of notation to write our domain and range. And heads up, I'm going to be a stickler for this. We need to make sure that we write these exactly in the right format. When we write things that are not in the correct mathematical format, it could potentially mean something different. And so we want to be clear in our communication and make sure that we're writing it either in what's this set notation or interval notation. So let's look at an example. If we said y is only greater than or equal to 3, well, look what we have here. What we say is, this is a y such that, that's what that line means, y is greater than or equal to 3. So this part is fairly simple. The part that a lot of people forget is to name the number system we're using. We're often going to be using the real number system, but in problem solving, we want to be careful. If we're talking about things that must be counted, like actual physical objects, we might have to use the natural or the whole number system. So just keep that in mind, that while we often use real, we might need to use something else. Let's look at another range, but let's look at one where it is in between numbers. For instance, y is always greater than -2 or less than or equal to 3. Look what they did here. They've added a few different inequalities. The first one they said is y is greater than -2, but y is less than or equal to -3. And notice what is really important here. They put the smallest number first, the -2, because in number lines, things read from lowest to greatest. So to keep things making sense, let's always put our lowest number to the right and our biggest number to the left. So let's make a little note. This is always going to be the lowest, and this is always going to be the highest. And we want to keep with that format. It makes it so much easier. Now, I think the interval notation is everyone's probably favorite because there's less writing involved. Remember, the square bracket indicates that a number is included. And that's kind of like on a number line. Remember when we did number lines and we had like something like this, and we wanted to say that 5 was included, and we would make a solid dot and say it was like, say, x is greater than or equal to 5. And then we would write something like this when we make this solid line here and put an arrow on it. Well, this solid dot to represent greater than or equal to is the square bracket in interval notation. Likewise, if we got rid of the equal to and just said greater than 5, well, that would change this number line thing. We would actually have a different symbol, and that's that open dot. Remember that? Those open dots? And then we would still write in the line. This means everything up to but not including 5. Well, that's what these round brackets mean. Same idea. So for a function where x must be greater than or equal to 3, we write, look at that, greater than or equal to square bracket 3. But notice what we put here. We put the infinity sign. Now, because infinity is not actually a number, it's a concept. We're going off to infinity. We use round brackets for that because we can never capture the end of it. It goes off to infinity. Now, if the function x must be greater than -2 and less than -3, well, then we have these definitive points at the end, so we don't need an infinity. But because it's greater than -2, we use the round bracket. And because it's less than or equal to 3, we use the square bracket. So -2 is the lower limit, 3 the upper limit, and there we go. And if you still need a little bit of help with set and interval notation, there is a link in the notes package that'll bring you to a short video. Now, I'll make a note of this now, but we don't actually need to hold on to this piece. It says, sometimes the context of a problem changes the domain and range of a function, and we must look at whether certain values in the domain and range make sense. For example, if the value of x represents the height of a tree, x, which is an element of the real numbers, would not work since trees can't have negative height, nor can its height be 0, because if there's no height, there's no tree. Therefore, the value of x in this context must be x such that x is greater than 0 or x is an element of R. Just keep that little piece of information about domain and range. It changes with the context of the question. All right, let's move on to example 4. 1/2 of the graphs of two parabolas are shown below. Identify the axis of symmetry, then use that to help you draw the rest of the graph. State the domain and range of each graph in both intervals and set notation. Well, the first thing is it says identify the axis of symmetry. So let me pull out some extra tools here. And let's draw this one right here. There's the axis of symmetry for this one. And while I'm at it, I'm going to put the axis of symmetry for this one. Remember, the axis of symmetry acts kind of like a mirror. It's like the graph is reflected in that mirror. So what does that mean by helping us to draw it? Well, what does a mirror do? Well, when we look at ourselves in a mirror, the person on the other side looks like it's the same distance from the mirror that we are from the mirror. So that means, for instance, if I picked a point, let's pick a nice one on one of these crosshairs. Let's pick that one right here. Notice this is 2 units from the axes. Therefore, the reflection of that point in this would look like it's on 2 units on the other side of that mirror. Where's another one? Oh, here we go. That's 1 unit, so this one has to be 1 unit. This one is 3 units, and this one is 3 units. So we have something that looks like this, and then if we use that, we can connect it all the way up. Let's do the same on the other side. Well, this one is 1 unit. Let's find another one that's on a crosshair. That one's that one. So this is 2 units. Here and here. And it doesn't look like we have any more that are on crosshairs. So this one kind of looks like it's 2.5. So, somewhere like that. And again, let's join those up, making sure that it's not connect the dot, but as smooth as possible. And right off the page like that. So now we're being asked to state the domain and the range in 2 different forms, set notation and interval notation. So let's look at the domain in set notation. Now let's think what that means. Because we have this thing going off to the left, so it goes up and to the right to infinity, and it also goes up and to the left to infinity. That means it continues to grow in this direction and continues to grow in this direction on this side. On this side, it continues to grow in this direction and it continues to grow in this direction. Well, remember, this direction here represents the domain, which means what is the upper limit of the x values? Well, it's infinity. Going in the other direction, what is the lower limit? Well, that is negative infinity. So when we want to say this in set notation, we just say we're using the real numbers, and we're going to do it just like this. So be sure that we have the curly brackets, the straight line separating the two parts of the statement. Now, what about the range? What is the lower limit of the range? Well, because this is opening up, the range has a minimum value of 0. But like I said here, it continues to go up and grow in that direction. So it goes to positive infinity. Well, in set notation, we're going to do the same thing as we did for the range, but this time we're dealing with the y's because it's those vertical values. So y must be greater than or equal to the lowest value of y, which is 0, where y is an element of the real numbers. Now let's make this into interval notation. Well, for a real number domain in interval, we're actually going to use 2 infinity signs inside round brackets. The left-hand side is the lower limit, which is negative infinity, and the right-hand side is the upper limit, which is positive infinity. Now, this is a little different for the range. The range has a lower limit because it's a minimum. So we're going to put that square bracket, 0, and then it's going to go off to infinity. It's going to keep growing in that positive y direction. Now let's look at the blue graph. Well, again, when we look at these endpoints here, it continues to fan out in the negative x direction. And on this side, it fans out in the positive x direction. So just like the first one, we're going to say x is a number, x is an element of the real number system. So x such that x is an element of the reals. For the y's, however, this now has a maximum. So we're going to write that one as the maximum value of y, which in this case is 3. So we're going to say y is less than or equal to 3, but we're not going to forget our real number system in this case. And let's do the translation into interval notation. This one is exactly as the first one. And this one is actually going to be a little different because this one here, it's going to go to negative infinity. It's going down as it grows. It's not going to be going up anymore. It's always going to be going down. So it's going to negative infinity. And then on the upper limit, it's going to be that 3. And it's included like that. Now I want you to have a try. I want you to pause the video again, and this time try question 2. And remember, if you're having any trouble, make sure that you email your teacher to let them know how things are going, or just to even let them know that you're doing well. They like to hear from you either way. Okay, now let's move on to do some calculator work. In this course, you will need an approved calculator. Some of the more popular versions are the TI 83, 83 plus, 84, or 84 plus. And the other one that I see quite a bit of is the Casio FX 9750. I won't read through all of these features. However, I do have these posted in the website under calculator tutorial. Rather than read these, what we're going to do is head on down and answer some questions where we actually will be using a lot of these features. Okay, question 5. A diver jumps from a 3-meter springboard with an initial velocity of 6.8 meters per second, her height h in meters above the water t seconds after leaving the diving board can be modeled by the function h of t equals negative 4.9 t squared plus 6.8 t plus 3. It asks us to graph this function using your calculator, then use your graphing calculator to answer the following. So first of all, let's get the calculator out. Now I do have the graph right here, but we're going to make sure we know how to do it on the calculator. So the first thing we do is go over into our y equals button. Now in a TI 83 or 4, we want to put that negative in first. Now you might want to put the subtraction sign in. We're going to hit the negative sign. In some in some applications, if you put the negative subtraction sign in for a negative, it actually gives you an error. So let's just get used to doing that right now. So we put 4.9. Now we're going to put in our variable. Our variable button is here, and we're going to use x for the t. We're going to square it. Then we're going to add 6.8x, and then we're going to add the 3. Now when we graph that, let's see what we get. Okay, looks pretty good. However, it's hard to see it. It's kind of hard to see that intercept, that y-intercept here. So we're going to change the window settings. Now the window settings is found in this button. So the window setting is too broad, so I'm going to tighten that up. So I'm going to make this -5 to 5 on the x and -5 to 5 on the y. And let's see how that looks. Sometimes we have to play with it. And there we go. Oh, notice here it's cut off a little bit. So I need to fix that again. Well, I also noticed that on the x, I'm going to shorten that up to -2. I'm going to keep this at, let's say about 3. The scale piece here, that tells you the jump. It's going to jump by 1. And on the y, I'm just going to go -2 here. Now this one I have to change and make it higher. I have to make it up to at least 6 if I want to see that little maximum peak. And I'm going to graph it again. So notice sometimes you got to play with these things to get it right. There we go. Now we can easily see things. So the first question asked is, what is the y-intercept? Well, we can do this algebraically, but we can also use our calculator. The way we're going to do it on our calculator is in the second calc value button. We know the y-intercept occurs when x equals 0. So we hit enter, and it tells us that the y-intercept is 0 and 3. Okay, so what is the y-intercept? It is 0 and 3. Notice intercepts are points, and you must state the x and y value. And if you can hear that, there's an ice cream truck going by my street. So what is the y-intercept and what does it represent? Well, at this point, this is time equals 0. Remember, it says that the person is on a board that is 3 meters from the ground. So in other words, this is the height at time t equals to 0. Perfect. So in other words, the time she began the jump at. Let's go to the next part. What is the maximum height of the diver reaches? What is the maximum height the diver reaches, and what characteristic of the parabola are you using to find this? Well, the maximum point would be this point right here. So we are going to be using the vertex to find this. Well, notice this little point is nowhere to be seen on the graph, like we would have to do a lot of estimating. But on the calculator, we can find the maximum point quite easily going back into that second trace function. And we're going to use number 4 for max. Now, the thing it's going to want us to do is get us close to the maximum point, but starting to the left. So notice it says left bound. So we want to make sure we're to the left. When we do that, we click enter. Then it asks us to go to the right. So we're just going to go over till we're a little bit over the hump and hit enter again. And now notice what it does. There's these 2 little arrows here. They're a little bit hard to see. Let me get that cursor out of the way. These 2 little arrows right here. They're saying, do you want us to guess? Yep, we want you to guess. We want you to figure out in between these 2 points where that maximum point lies. You hit enter. Oh, and it says a bound problem. Let's see what that's all about. Second trace, 4 for the maximum. Let's try that one more time with feeling. Enter. Enter, enter. There we go. Not sure what we did wrong first time. And by we, I mean me. But it says, what is the maximum height the diver reaches? Well, that vertex as a point is 0.69 to 2 decimal places. And the height is 5.4 to 1 decimal place. So let's look at that again on the calculator. So 0.69 and 5.4 because that 5 rounds that 3 to the 4. Okay, so let's type that in there. So the maximum height the diver reaches is, oh, let's see, 5.4. Oh, and it's 5.4 what? Well, that would be in meters. So we have to make sure when we do these word problems that we include not only the correct rounding of decimal places if it asks us to, but also units. So the next question, C, says, when does she reach that height? Well, let's remember that the time is the x and the height is the y. So in other words, the x coordinate at this point is the time she reaches it. And according to our information, that would be the x coordinate of the vertex. In other words, at 0.69 seconds, she will reach the maximum height. There we go. Now part D. How long does it take before the diver hits the water? What characteristic of the parabola are you using to find this? Okay, when do they hit the water? Well, remember, h is the height above the water. So when they hit the water, the height is 0. So in other words, we are going to be using an x-intercept to figure out the time. Now, we know the y value of this is 0, but we don't know what time that happens at. So we need to go back to our calculator, and we're going to find the coordinate of this. And the way we're going to do that is back in that favorite trace, and we are going to look for 0. 0 is just another word right now. We're going to explain it later on why it's actually called a 0, but 0 is the x-intercept. And just like a maximum, you have to go to the left and to the right. If it's going down and to the right, you're going to be above the x-axis first, and you're going to hit enter. So notice we got a positive y value. Then we're going to go till we get a negative y value. That means we're to the right of that intersection, and we hit enter. And notice we have those two arrows pointing, and we're going to hit enter again. And it says the height is 0 when the time is 1.73. So we can write that down as at 1.73. Oops, we got to look at the rounding here. That's a 9. So that means it's going to be 1.74. So she will hit the water at 1.74 seconds. And there we go. Now, let's talk about domain and range. This is a perfect type of question to consider that domain and range may change depending on the context of the question. For example, in this question right here, we know that time cannot be negative. We're starting at 0 and moving forward in time. Furthermore, the time does not go past this point here, because once they hit the water, everything stops. The dive is over with. So in this case, the domain, and we'll write this in two types of notation. Let's do the domain in blue. Time can definitely equal 0 because that's where she starts. And time can definitely equal that 1.74 because that's where she finishes. So we can write it like this for the domain. Or we can write it in interval notation. And in interval notation, x such that x is less than, oops, we got a lower domain here of 0, less than or equal to x, less than or equal to 1.74. And we must state that it is the real number system here because time is a continuous value. It's not discrete. It's not countable in the sense that nothing happens between 1 second and 2 seconds. For instance, there's all kinds of times between 1 and 2 seconds. So it's real, it's continuous. Now, what about the range? Well, what is the minimum height above the water she can be? It's 0. She can be at the water. We already determined this by this intersect right here. But what is the maximum? Well, the maximum is here with that height of 5.4. So the range can be between 0 and 5.4. In other words, in set notation, same idea. 0 less than or equal to y less than or equal to 5.4, where y is an element of the real numbers. That's because height is also a continuous measurement, because even though we can have 1 meter and 2 meters, you're always going to reach those values in between. And let's look at the last two questions here. In this one here, part F, it says the height of the diver 0.6. What is the height of the diver 0.6 seconds after leaving the diving board to the nearest hundredth of a meter is? Now, what I've done here is I've put this as a numeric response type question. We're going to get used to doing numeric response type questions because they're going to come up on quizzes as well as exams. So let's break out the calculator. And we want to know the height of the diver at 0.6 seconds. Well, this is a time value, t. In other words, t is kind of like x. So we can use second trace. We can use that value right here. Because remember, time is on the x-axis. We can put 0.6 right there and hit enter. When we do that and we write down our answer, we get 5.316, but it says to the nearest hundredth, so 2 decimal places. So we're going to take that one and round it to a 2, and we're going to write this as 5.32. Now let's look at part G. In part G, we're now given a height, and they're asking us to find a time. Well, how can we do that? The easiest way to do it is actually to make a second graph in the height that they give us. And so what this means is we're going to get a horizontal straight line going through 2.5. And we are going to find where it intersects the graph. Now, as you can see, it actually intersects the graph. Oops, it's not going to let me do that. Yeah, definitely not going to let me do that. I don't know if you can see my cursor, but a little bit over to the left of the y-axis. Because the value of x for that is going to be negative, we don't care about that. We're concerned about this other intersection point here, and the way we're going to find what that ordered pair is go second, trace, and 5. Now, we're just going to head on over closer to this intersection point, because what the calculator does is it will pick the one that's closest. And originally we were over here closer to the first intersection. We don't want that one because it's not in our domain. So we're going to pick that one, and I'm going to hit enter. Then notice it actually jumped over to that line. Remember, that line is y equals 2.5. So we're going to hit enter again to say, yeah, those are the two lines that we want to find the intersection of. Then it asks us to guess, and we're like, yeah, we'll guess. We'll play your game. And when y is 2.5 meters, the time is 1.4577 seconds. And so in this one here, to the nearest hundredth, we're going to say 1.46 seconds. So go ahead and 1.46. Perfect. And again, that would be like a numeric response question. Now the last two things. 1, let's do another quick check-in. Try questions 3 to 5. Check your answers at the bottom and let me know how it goes. This is important because I want you to be comfortable asking questions of your teacher. Let them know if you're doing well or if you still need some help. They're going to be more than willing to help you out. After you finish those, just keep on going. Do all the practice questions. Remember, it's a great way to learn the material, and it's going to boost your confidence. The more you do and the more you get right, the more confident you'll feel, and you'll want to keep moving forward. If you have any questions about the video, if you have any questions about any of the practice questions, remember, always get in touch. I hope you have a great rest of your day.